from Lawrence Berkeley National Laboratory. So if you are ready, please start your presentation.
Can you see this?
Yes,
Great.
please.
One second, trying to get this to go into full screen. Okay. Yeah, thank you so much for that introduction. I'm Craig Schwartz, and I'm going to be talking to you today about new measurements, new X-ray measurements on water. So this is a particularly weird talk for me because I'm not actually going to be talking about my own work. In the past 2 years, we've only had one measurement on water, and it didn't work. And while in all likelihood, if the world hadn't blown up the last year, we would have made the follow-up measurement. But this is strange times, so I don't have any new results on water. But there have been some really interesting results on water I'm pretty excited to talk to you guys about. So I'm going to go through, and what I'm going to do is I'm going to introduce you guys to sort of X-ray spectroscopy and the sort of way we use X-rays, their uses for both spectroscopy and scattering. I'm then going to pivot and talk to you briefly about why some of these new measurements are able to be made, focusing on the fact that we have some new machines which enable us to do some new measurements. Then I'm going to talk in detail about a paper doing some spectroscopic results on water at ambient conditions from Alexander Folisch at the University of Potsdam, and then 2 papers from Anders Nielsen's group at the University of Stockholm. And I'm ultimately going to sort of leave you guys with a puzzle. I'm not going to come up with a nice sort of conclusion because the papers don't totally agree. And maybe that can be an opportunity for someone listening to actually make some progress because I don't really understand what's going on. All right, so to the beginning. So this right here is the molecular orbitals of water. And if you were doing, say, visible or UV spectroscopy, you'd be pushing these electrons into these orbitals. In in X-ray spectroscopy, you tend to push around these low-lying 1s orbitals. So we just look at the oxygen core hole orbitals, and in particular, for something like X-ray absorption, what you're going to be doing is you're going to be pushing the 1s orbitals here into these non-bonding and anti-bonding states. So for water, it goes from about 530 eV on up in energy. You can also do the opposite of that, and that's called X-ray emission. What you do is you take you put in so much energy that the electron is effectively gone, and then you watch these electrons fall back down. Now, those of you who are paying close attention probably already guessed that you can combine these techniques and you can make sort of a 2D chart that's called RIX, which is resonant inelastic X-ray scattering. One thing to note, though, is that X-ray emission spectroscopy is not instantaneous. So X-ray absorption or RIX happen more or less within something like 20 attoseconds and no movement can take place. X-ray emission spectroscopy, after you ionize the water molecule, you have this state which exists for something like 7 femtoseconds on average. And that's not a lot of time, but it's enough time for a water molecule to move. And so you can start seeing those sorts of effects. And we'll get into that in a second. The other thing I need everybody here to understand is some basics on scattering and only really basic things. I would guess that everybody here has at least some familiarity with crystallography. This is where you shine X-rays through a crystal and you get a bunch of spots, as you can see in this figure here. And you can use these spots to, if you wanted to, sort of assign the structure, but we're not going to be so concerned about that. It's mostly just that you get a lot of spots in specific areas. But you can also do this same technique with say, liquid water or anything that's not well defined, and then you get something called Sachs wax, and then you get sort of broad peaks. But it's the same idea. It's just you're doing it on something that's not a crystal. All right, so let's begin at the beginning. Oh no, I forgot about this. I want to take a second to talk about how we make X-rays. So for those of you in Japan, the closest synchrotron to you guys is at Spring 8, which is about an hour and a half south of Kobe. And these are large-scale facilities. They give you a very good average power, but they don't give you a ton of power in a very small amount of time. So if you're particularly interested in phenomena that are really fast, these aren't great. But there's still the workhorse machines, and they get used all the time. But recently, and there's another one of these also on campus with Spring 8 called SACLA, we've been building these new machines called X-ray free electron lasers. These are billion-dollar lasers, and what they are is sort of a particle accelerator tied into an X-ray device, and they give you all the power you get out of a synchrotron in a second in something like 50 femtoseconds. So it's much, much faster, much, much more intense radiation. These are really wonderful machines, but they're expensive. But they do enable you to learn new things, which I'm going to talk about today. All right, but first we're going to start with the basics, which is this is the X-ray absorption spectroscopy of gaseous water in blue. It's this line right here. Of liquid water in black. It's this line right here. And ice in green. And these spectra have actually all been taken before. These are just, all they did that was new in this paper, this is the paper by Alexander Froelich, was they normalized it slightly differently, but even then it doesn't matter that much. But they basically interpret it by saying this region, they call it 1, is very sensitive to donated hydrogen bonds. You know that ice donates 2 hydrogen bonds and that gas phase water donates 0 hydrogen bonds. And if you look at the liquid water down here, you can see that it's much, much closer to ice. So therefore they argue that it gives you 1.74 hydrogen bonds. This sort of implies that there's a linear dependence to donated hydrogen bonds. This is larger than some previous studies, but it's in line with those that haven't done calculations. The people who have gotten vastly different numbers have been doing it based largely on calculations. So this is sort of an answer you might get from like 50 or 60 years ago, and this aligns with that. They also looked at the X-ray emission spectrum of the liquid water. And this is this sort of 2 blobs here between 528 and 524 electron volts going this way. These have been shown previously. There's 2 bumps there, as you can all tell. There was an argument in the literature at one point that this was indicative that water was actually 2-state. This sort of fell apart a couple months or a couple years ago when somebody measured the spectrum of ice, and that's definitely not 2-state. Ice is definitely a single state. And they also saw these 2 bumps, but it was sort of unexplained for why this was. They did a nice job of going through and explaining that this is almost certainly due to those excited state dynamics. So you start with with an oxygen and a hydrogen, but after you excite that oxygen atom, you can get motion on the timescale of a couple femtoseconds, and in those couple femtoseconds, you can get dynamics, and those dynamics can lead to the second peak, is their argument. And I think this is sort of well sourced. The final measurement they made was doing RICs. So what they're doing here with RICs at energies between 545 and 534 electron volts going in, what they're looking at here is the energy that you lose. So you can see here a vibrational spectrum, sort of a vibrational progression as they go from, you can see the first, the second, the third, and all these excited vibrational states. And you can actually use this to make sort of a Morse potential. So you can plot all the energy levels, and they do this for gas phase water over here in B, and they do the same thing for liquid water in D. In both cases, you can actually line them up on the same potential. The only difference is that liquid water is quenched, which is expected. So you end up basically getting a thing that can be fit with a single Morse potential. If you've ever done this exercise in undergraduate Gen Chem, it's, here's a bunch of vibrational states, fit the potential, and they do this. And that it can be fit with the same one for gaseous water and for liquid water, they argue strongly implies that you have a continuous, well-behaved single state of water. And so taken as a whole, what they argue in this paper is that that water is a single state, well-behaved, well hydrogen bonded liquid, which is sort of the argument that was really popular maybe 50 or 60 years ago. And if that was all I was going to present, this would not be a very confusing talk, but it gets confusing when we go to the next couple papers. All right, so this is a paper by Anders Nielsen, and I need to explain what they're doing in this paper. So in this paper, they're taking droplets of water in either H2 or D2O. They're going to do both of them. And they're using evaporative cooling. So they're taking water droplets that are, say, a micron, and as you inject them into a vacuum chamber, they automatically cool off from the evaporation. And so this allows you to get a very well-defined temperature as a function of how far down you are. And they're doing this, and what they're going to do is they're going to probe it with X-ray pulses. And so this is why they need a free electron laser, because they need to be able to know which drops are frozen and which drops are still water. If they're a frozen droplet, they're going to toss it. But if it's a liquid water droplet, they're going to plot the SACs and WACs as a function of energy. SACs is the small angle X-ray scattering, this stuff here. WACs is the wide angle X-ray scattering here. Very, very loosely, you can say SACs corresponds to isothermal compressibility, and WACs is related to tetrahedrality. All right, this is where it gets weird. So they plotted here from 255 Kelvin on down to 227 Kelvin, and this may be a bit hard to see, but it actually turns around. So it goes up until about 229 Kelvin, and then it turns back around and goes the other direction. And you can do this by either integrating or by extrapolating it to 0. It doesn't ultimately matter. You still get the same effect of a very strange, not consistent with the previous paper. Admittedly, this is at super cool temperatures, but still it's not consistent with what they saw previously on water. And they see this for both H2O and D2O. And so this is not very single state behavior. I think everyone would agree. All right, then they also look at the wide angle X-ray scattering. This one is a bit less weird in that it at least doesn't turn around. As you go from 255 to 227 Kelvin, the peaks do get closer together. And they show this by plotting the derivative of what they're calling S of I, which is the top of the peak, versus the derivative of the temperature. And again, at about the same temperatures, 228 Kelvin for H2O and 234 Kelvin for D2O, you again see something turn around. And again, this is not consistent with that previous paper. So they try to do some more explaining on this. Sorry, jumping ahead. And they're actually able to fit their whole data. So their data here is the black line, and they're able to fit it using a two-state, or basically a two-step model. It's not two-state. And so they basically get excellent fits, and the fit consists of two steps. The first is this green fitting, which is based on hard sphere theory, where this would do what you would get basically perfectly if you did this for liquid argon or for like liquid ethane, a very simple liquid. You get this sort of green line, and that actually corresponds to the isothermal compressibility, as you see over here. Again, it's peaked, as you would expect. Maybe the more interesting thing is that they can also relate it to the sort of interactions of water, which can be displayed as a function of correlation length. And this goes again at about 229 Kelvin and 233 Kelvin for H2O and D2O. They get basically an excellent fit. So this implies strongly that there's at least something like a liquid-liquid critical point, or that there's a critical point deep in the supercooled region of water, which of course raises the obvious question of why didn't we see that in the ambient water that we saw in the previous paper? And I don't have an answer to that. But they're not done yet. The Anders group went through and did some more measurements. This is a sort of separate paper. What they're going to do here is they're going to start with amorphous ice, which is basically ice that's not well crystallized, and they're going to hit it with a 2-micron IR laser. This is two things. Number one, it rapidly heats the sample, and number two, it rapidly pressurizes the sample. The pressure will then drop much more rapidly than the temperature, but since you're starting, you're going to see this drop over time. You don't have them, neither of them are well calibrated, but you start from 200 Kelvin and you go way above that in temperature, and you go way above 1 atmosphere in pressure, but they don't exactly know how much. And then what they're going to do is they're just going to plot the Sachs wax. And what's nice about doing this with an X-ray probe is you can tell when it's crystalline ice because you get these really sharp peaks. Okay, so then what do they actually see? All right, so they're doing this for two samples. One's a thick sample and one's a thin sample. The thick sample is 45 microns thick. The thin sample is about 20 microns thick. And they're starting with, okay, so the color scheme here is gray is what they're calling high density liquid, which is that high density amorphous ice they started with. Red is this state, which is not crystalline and not the gray one, and basically a mystery. They're calling it a low density liquid. And the blue one is crystalline ice. And so what happens, and the time scales here are important. You start, and in about a couple nanoseconds, about 20 nanoseconds or so, you start to see this low density liquid form. Out to about a microsecond on the thicker sample, or at about 3 microseconds, you start to see crystalline ice form. By the time you get out to a millisecond, you're dominated by crystalline ice. But these are very different time scales. You're looking at 3 orders of magnitude here between when the low density liquid and when the ice forms. And this implies strongly that they're separate thermodynamic phases. They also do this, by the way, with the thinner sample, and the time scales are different, but this isn't actually interesting. It's just a function that you can heat the thinner sample more because there's less of it. So it's the same phenomena. There's nothing crazy going on there. Yeah, so you can actually plot this as a sort of a function of time. And so you can see right here is the high density liquid that they start with. And over time, by about a millisecond, you have none of it. And the opposite is true with crystalline ice, where it goes from basically having nothing, but at about there you start seeing it rise in at about a nanosecond or about a microsecond. And then by 10 microseconds, it's dominant crystalline ice. But with this low density liquid, it immediately forms, so it's something like nanoseconds, so really short on this time scale. And it peaks at about 5 microseconds, and then it goes away, implying that you're probably getting something like a first order liquid-liquid phase transition. And the reason you think you can argue more strongly it's a separate phase and not just something they assigned is you can actually look at the small angle X-ray scattering. And in general, with this sort of plot, homogeneity is, so a very homogeneous system is down here at the low values. And so this is liquid ice, or ice at the very end is going to be very homogeneous, right? And the amorphous ice you start with is relatively homogeneous. But in the middle here, you have something that's more homogeneous or more inhomogeneous. So you have multiple phases. You have something weird going on here, which is really only consistent with a new phase being formed. So yeah, this is sort of the puzzle I'm leaving everybody with. I don't have a great answer to these questions, but basically we've shown at ambient temperature, X-ray spectroscopy points to a continuous single state of water, strongly hydrogen bonded. But if you look at the X-ray scattering in the deeply supercooled, but at ambient pressure, it looks like you have some sort of liquid-liquid critical point. If you rapidly heat amorphous ice and get to a different pressure, before rapid crystallization occurs, you get a different phase, which implies strongly a liquid-liquid phase transition. And these results appear on some level to be really contradictory because it's not clear where this first order phase transition doesn't extend so well into the X-ray, into ambient conditions. And so, yeah, this is where I'm going to sort of hand it off to hopefully some clever experimentalists who have some new ideas. So you can do some really easy things like going to different pressures, but there's other more clever things you could possibly do. You could start thinking about doing simultaneously X-ray probing, and for those of you, because I know you're really interested in near IR work, if you could probe at the same time doing that, you might be able to say some things about it. You can do all sorts of nonlinear methods. For those of you who love lasers, you can start doing things where you correlate 2 or 3 lasers together, maybe getting really fancy. But I don't really have a take-home message other than that there's a lot we still don't understand about water, and these papers, I think, really indicate that well. Yeah, so this work was not mine because we haven't been able to make any measurements on water. So I want to thank the Foley's group in Potsdam and the Nielsen group in scattering for doing this. If you have any questions, feel free to email me. And with that, I think I kept it under time, hopefully.
Thank you. I have a question.
Yeah.
Sensei. Okay.
Sorry, I forgot to remove mute, please.
Okay. I myself also continue being interested about what you said, the phase, how many states water has, and all this discussion. To me, and what we, at the moment, we are not discussing this at all because we accepted what we see experimentally is that water presents itself as a bunch of specific conformations, water molecular conformations that change the ratio depending on the surroundings, the environmental temperature, pressure, humidity, etc. What do you think about this?
Yeah, I mean, these are the difference between these papers is just the temperature and pressure. And yeah, but you'd think it would extend out. I guess what's hard to understand is why it doesn't continue in the sort of longer time scale. That's what I don't have a good answer for. But yeah, I think that the answer that you're giving is basically correct, but there's a lot to that answer, right? Like there's, what I'd like to be able to say is like at this given temperature and pressure, this is what's going on, and we can't do that.
Yeah. Yeah.
That's I guess that's the confusing part, is like what is actually going on, and I don't have a great answer.
Now another question is about using 2 types of light. Obviously, so we know that light affects water. Using lasers and using a simple halogen lamp makes a difference. This is what we observe. But is, to your knowledge and X-ray community, do you have this in mind when you do your experiments? Coherence of water and the relation between water coherence and laser as a source of light?
So the second set of measurements, all the scattering measurement, you don't really absorb any of the light; it just goes away. So the source should matter less on that, like, because that's basically lossless. Mm-hmm. So it shouldn't matter that much for that. That's a good question for the sort of spectroscopic stuff, though. Mm-hmm. And I didn't do this analysis, so I don't want to plead ignorance, but. I don't know exactly how they see. A lot of this is really conceptual, like what they're doing, and not into so much math. So I don't know exactly. So I hate to give a I don't know a ton, but that's my answer for the first part.
No, but yeah, thank you. Understand. What I was fascinating when you saw this slide exactly. What is really fractal? So we wrote a paper about fractality, proving fractality of water. But it's so interesting that we see the same signature of water in different regions. So an aquaphotomics conference, so that's why we discuss X-ray, terahertz, infrared, and we see the same pattern all over, which is interesting in a way. But what you said, and I would love to do this, to incorporate different techniques and do simultaneous measurement. An infrared is non-destructive. Well, not 100%, of course.
Less destructive, I would say. It's definitely less destructive than these X-ray measurements which blow everything up.
Yes, it is less destructive, but at least so we should do this hyphenated spectroscopy in the future.
Yeah, I think that would help a lot because right now there's just not enough to know what's going on.
Yeah. Thank you very much indeed.
Can I also have...
please.
Thank you, Professor Daquit. Craig, as I said, I will have questions about your lecture. So Professor Tenkova touched upon this difference between the light sources used, the techniques of measurement, but I also noticed today that actually your sample, the samples that were investigated are, in my opinion, different. They're produced in different ways. So we have here evaporative cooling. Then the other experiment was about actually heat rapidly induced by infrared laser. And for example, I noted that if there is a pulsed infrared laser working, the length of the pulse influences the changes. And we definitely saw differences in the water behavior upon cooling and heating, like a hysteresis behavior. So I was wondering, are we maybe looking at just different phases, different samples?
Yeah, I mean, so certainly when you heat with the infrared, it's different in that you're definitely adding pressure, right? So I think the biggest thing there is going to be the pressure jump when you dump in that sort of 2 micron ultrafast laser is enormous. You're probably going from, atmosphere to, maybe megapascals sort of pressures right away. And then you're starting to release that, and those sorts of pressures, I think, are going to, like anything else, is going to be swamped by that large pressure jump. So those effects are probably real, but I think you're not going to, the bigger effect is the pressure, I think, especially for these.
Yeah, that must influence. We had some experiments with that. Thank you, Craig.
Okay, time is over, but I have a small question.
Yep.
Is it possible to obtain the information like X-ray absorption, fine structures, for example, for ice samples?
So I didn't take that data, but you can email Alexander. Do you want me to get you I can post in the chat the corresponding author for that paper, and then you can email him. It should be available. It's not, it might even be in the paper itself. I'm not sure if they did it. It's in one of those journals though where they say you have to give it up. So we should be able to get you the data.
Okay, thank you very much. Okay, so now let's move to the next speaker. Thank you, Craig. Next speaker is Professor Shigeaki Morita from Osaka Electrocommunication Universities. To keep his presentation time, I will just introduce